Look at this diagram. It starts as a single white square, but we can only measure its behavior if we stop viewing it as a static object. Instead, watch it grow. Much like tree rings forming over time, each new iteration adds a complete outer layer to the perimeter. If we count the individual squares making up these new layers, a strict mathematical sequence emerges. The first new layer adds 4 squares. The next layer adds 8. The layer after that adds 12. This pattern is driven by the geometry. The shape expands outward in exactly 4 directions: up, down, left, and right. Because every new layer builds along these 4 distinct edges, each successive wave requires exactly 4 more building blocks than the one before it. We can capture that growth algebraically. For any given iteration we call I, the total number of squares added in that specific step is simply 4 times the quantity I minus 1. By translating this physical expansion into a predictable sequence, we no longer have to manually count individual blocks. We can calculate the total size of the shape at any scale. Now, we need to figure out the grand total of all the unit squares combined across a target number of iterations, which we'll call n. We start with our original center square and then add up every outer layer we've built. Look closely at the sequence we just generated. After that initial center square, every subsequent term contains this recurring multiplier of 4. We can simplify the series by extracting that 4. We pull it outside a set of parentheses, leaving behind a clean string of ascending digits. This factoring clears away the visual clutter, but it leaves us with an arithmetic sequence inside the parentheses that is still too long to solve manually for large values of n. We need to compact it. Let's focus on that inner sequence, 1 plus 2, all the way up to n minus 1. We need a way to turn this string of additions into a single tight fraction. We can group the terms to find a shortcut. If we take the first term, 1, and add it to the last term, n minus 1, they combine to equal exactly n. Move one step inward. Take the 2 and add it to the second to last term, which is n minus 2. Those also sum to n. Because we are pairing terms from the outside in, there are exactly half as many pairs as there are terms in the sequence. That gives us our multiplier, n minus 1 divided by 2. We can now replace that entire long sequence with this proven fraction and plug it back into our master equation. We have successfully collapsed a problem of geometric growth into a single solvable algebraic statement. This is a great place to pause. Grab a pen and a piece of paper and see if you can expand and simplify this raw polynomial on your own before we finish the proof. To simplify, the 4 and 2 cancel, leaving a 2. Multiply the n variables to get 1 plus 2 times n squared minus n. Distribute the 2 for our final formula, 2n squared minus 2n plus 1. This predicts the square count. This algebra is the standard way to reach the answer, but the geometry hides a shortcut. Watch what happens to those jagged staircase edges if we rotate the entire shape 45 degrees.